Good afternoon, everybody. I'd like to speak to you today about the application of composite materials to eliminate corrosion in marine environments. My name is David Taylor. I'm the Vice President with SECO Peerless, based in Dallas, Texas. And before I get started with the agenda, I'd like to introduce somebody in the audience today, Mr. Alex McAnder, formerly of Carderock, currently retired. And I consider him to be the godfather of composite louvers. So we have a master in our presence. Learned a lot from Alex, and a lot of what he did in previous research is referenced in my paper, so you can look at that in a little more detail. But really, he is the foundation for a lot of the work that we're doing today to support the Navy. We'll talk a little bit about what's the reality aboard ships these days. Corrosion is everywhere, and I'll give you some examples of that. And some of the challenges in working with how do we deal with corrosion, right? So there's ongoing maintenance. You repair things, you replace things, and then the question of, do I replace it with something that I had before, or do I make a switch and say, hey, I don't want to do this with steel. I'd like to do this with FRP composites instead. And some really good payback examples and weight savings examples that I'll share with you. We'll talk about the manufacturing method. Early processes were a little difficult to keep on schedule, poor for delivery, and then a little bit more flexible manufacturing that's available to us today with pultrusions. Some examples about the AKE ship and the LPD ships, which have two different types of composite louvers, but they both perform to the needed specifications for those ships. And finally, we'll talk about what are some other future opportunities. So we're very focused on louvers now, but there's other things, of course, that can be dealt with to try to deal with the corrosion challenges. So here's where we are today. These are actual photos I've received from colleagues that are aboard ship or in Carderock or NAVSEA. Typical activities aboard the side of a ship, you see them, they're staining on the sides of the ship. It's pretty embarrassing when you first look at it. You wonder why is such a beautiful ship having these challenges and going around the world like that? But look in the center lower piece. That's a typical intake louver. That is in a very bad state of corrosion. The blades on that louver are similar to a Venetian blind. Typically they're not moving, they're static, but they are corroded completely away. So it looks bad, it creates a safety issue, and it also doesn't perform its intended function, which is either separating moisture or protecting a workspace. So lots of hazards that are generated through this corrosion. They're typically protected with screens. So you see a picture of the screen that's in front. Those are typically stainless. They might be painted. They might have a special coating. But those can also be done with composite material. And on the far left side for you is a close-up of blistered paint. So that's kind of the first sign you see. As the base material, the steel, starts to corrode, the paint will start to blister and chip away. What's the first thing that is typically done? Well, it's grinding or brushing to try to remove that paint and repaint it. But at some point in time, that repainting is useless because the base material is eroded away completely. In addition to just dealing with the work itself, so if you're removing a louver or replacing blades, in a workshop it's always easier than aboard ship, but the challenges we face in the ports are numerous. You've got situations that are difficult to access. You may have to get 2, 3, 4 stories above ground level to access these louvers. So hydraulic lifts are required. Associated with those hydraulic lifts, you're going to have a safety crew at ground level to keep people away so no one gets anything dropped on them like a tool or a person or anything like that. So it's not just the work at hand. There's so much more that goes into this, and it's not just the time for those pieces of equipment, the money for those pieces of equipment, but the time it adds to the schedule. So time is money, and again, dealing with these situations to repair, they just become very difficult. The other picture I'm showing, you can see some cabling going through one of the access openings on the side of the ship. So those are the hydraulic or electrical cables that are required for the tools, or maybe for the welding equipment. So again, you've got to figure out, how do I get this stuff through the hole? How do I get my machinery into a tight space? I'm avoiding overhead piping, raceways that carrying cables, and everything has to typically get through a small manway just to gain access to the louver itself. So the work is very, very challenging, and then hopefully the weather's treating us right so we don't have to deal with other things like extreme heat or other bad weather conditions. There's a very practical way to avoid this problem, and that is to apply FRP composites instead of steel. So we've seen many aspects of louvers in various states of disrepair. The composites, of course, don't corrode. They can be painted or treated with a surface coating to match the ship, whatever color it may be. And they can also have special treatments to give the material properties for safety, such as the inability to catch fire or the inability to propagate a flame. So as many of the FRP experts know, you can put chemicals in. We'll share a little bit more with that in a few minutes. The units that are being applied for the LPDs and the AKE ships, they are already accredited and certified to MIL standards for shock and vibration. So they've been tested. They've been tested for wave slap, flame spread, smoke generation. So they're going to be safe, they're going to be robust, and they're going to do their intended purpose just like a steel part would. So we'll talk in a few minutes about the benefits of the FRP. And the main thing in terms of that, additional to the lifetime, is the ability to save weight, right? So we'll talk about some of the payload advantages aboard the ships in a second. I mentioned the early days of applying composite materials. A lot of that was done with molded pieces. So molded pieces are custom designed. They require a different mold for every piece, and that becomes very expensive, especially on shipboard applications for louvers. The openings on the side of ships vary in size from 1 foot by 1 foot to 10 foot by 10 foot or even bigger. So every opening is a different size. There's no rhyme or reason that, to my awareness, to say this is the size, we're going to standardize these sizes of the openings. We have seen hundreds of different sizes of louvers. So the ability to use a molded plastic, it just doesn't make sense. What we're doing instead is we're using pultrusion. So pultrusion, we can make essential shapes like the frame, the louver blade, and the spacer blocks that go in between. So you really only need 3 or 4 different molded parts. You produce those into long sticks of that given cross section. So you can see up here a very complex cross section. That's the frame, and that's for one of our LPD louvers that has the tongue and groove type of assembly process. So whether it's a simple rectangle, a simple angle, or a complex shape that's going to have interfacing parts, that can all be done with pultrusion. So the key here with the pultrusion process is we bring in the raw materials. So you have either a rope or a fabric mat, which is introduced at the entry to the procedure. It goes into a resin bath where it combines with the plastic, goes through the heating and curing process, and comes out in its hardened state with the right shape. And during that, you're pulling the material through, and when it gets to the end, you can simply chop saw to cut it to the length, and then deal with those pieces and get them ready for the next stage of production. In the lower pictures, you see some of the fit up of the parts after they've been cut to length and machined. We do a processing where, in this case, the tongue and groove, where the louver blades are fitting inside the frame. They're integrated and nested against each other, and then they're held together with epoxy. I'll show you a little bit of a quick video snippet of the pultrusion process and give you a little bit of highlights what's going on. So this is the raw material going in this case, either string fibers or fiber mats. Those are selected based on, of course, their fiber size and the ply schedule that's required for the part. And they all feed in together into the pultrusion machine. They are combined with the resin, and then they produce big long sticks of pultruded parts at the end of the day. You'll see here in a second some of the chemical additions that can be done. Alumina trihydrate can be added for some of the smoke resistance and fire resistance processes, and that's really what gets us up to spec to meet the safety requirements on ship. So once we get the parts in their raw form as pultrusions, the next step is to try to say, well, how do I make this into an intelligent shape? And I'll give you 2 examples. So on the AKE, we did more of a generic louver. These are simple, more simple connections of square corners. So rectangular louvers or square-shaped louvers, and much more simple to put together, and still using the same pultruded parts. In this case, we were trying to serve the AKE ships that had a variety of sizes, and the size here, we had a FOD screen, or foreign object debris screen, which is typically a metallic screen, and we converted that into a molded grating made of FRP. So this actual device was 100% composite. We had no steel in it whatsoever except for the bolting that is attaching it to the ship. The idea on this ship was to create something more simple and quick to install. One of the challenges we face is an opening on the ship that has radiused corners. So radius corners are very typical from a structural design standpoint, but we're trying to fit a square peg into a round hole, or do we do it another way? And what we decided was to do it another way. So working with Military Sealift Command, we went aboard ship, we worked with the engineers and decided that let's put it behind the wall. So we can actually put this square piece, slightly oversized, behind the cutout in the wall and attach it on the back side. So this was a much more simple approach. It allowed us to use square cut ends and create a very robust design that was economical for that application. So the louvers were on the back side and the FOD screen is on the inlet side of this device. The LPD was a completely different story and a much more advanced type of design. This is the one that Alex was very integral in the early design. The additional feature on this approach was to use radar cross-section material, or RCS. So this was a layer, a carbon veil, which is installed inside the pultrusion, and that acts to absorb or reflect the radar so that the parts ultimately had the same or similar radar signature to the side of the ship of the LPDs. A little bit more complex design, especially in the corners, where we mimicked those radiused corners with pultrusions, but in short transitions. So those transitions were interlocked with dovetail joints and held together with epoxy adhesive. This is a little bit more challenging because every corner is unique. So when you're doing dovetailed machine joints where you have parts interlocking with each other, those angles are critical. So imagine a 5-axis CNC machine cutting the ends of these pultruded pieces and creating dovetail joints or puzzle pieces on a series of angles. So everything was tightly controlled. There's a lot more time required for dry fit up of the parts during manufacture before you start doing any adhesive. But ultimately, you get that sorted out, and then you can glue everything together into a final louver. This device actually still uses a stainless steel FOD screen mounted to the backside. In this case, it was a perforated plate. And those were devised in either one piece or multiple pieces, depending on the size of the louver. So we weren't able to achieve 100% FRP on this product, but we were able to isolate the stainless steel from the side of the ship, so it's in an interior space. So what does weight savings really mean? I wanted to share a few practical examples of what the weight savings that we were able to achieve for LPD and AKE. So LPD, depending on the number of louvers, there was a savings compared to steel of anywhere from 17 to 28,000 kilograms per ship. So just by changing from one material to another, that weight savings was realized. And it wasn't even the full set of louvers on that ship. So what does that mean? If you look at an F-35 jet, 10,000 kilograms. If you look at 13 Tomahawk cruise missiles, that's another 20,000 kilograms. 80,000 phalanx rounds, or one amphibious assault vehicle. So these are the kind of things on an LPD that could be moved in addition in cargo just by changing the weight of your louvers. So a pretty practical, pretty simple exchange of kilograms for kilograms. Aboard the AKE, I learned a really interesting lesson. Of course, many of you know that those ships are basically taking replenishments out to sea, and I really understand the value of milk after being on that ship. So I used milk as an example here. Milk is a rarity or a scarcity aboard ships at sea, so if they can get an extra 2,000 kilograms of milk, I think we'll have some happy sailors. Back to the cost, back to the lifetime maintenance. So the cost of corrosion it's real, and independent of all those auxiliary costs of cranes and safety and all that, if we just look at the heart of the matter, which is repairing or replacing louvers, the cost difference and the cost savings is tremendous. A typical example aboard AKE, approximately 30 louvers, and I averaged it out to their average size. If we look at that example, there were three options in front of the port engineer. One was just, I'm going to continue maintaining. I'm going to cut out pieces, replace them when I need them. I'm going to paint. I'm going to have my guys working on this, other people working on that. It's a constant battle against corrosion and against fixing the product. The other option was I'm going to buy new stainless steel louvers and just do the same thing again. I'm just going to kick the can down the road, and I'll start the cycle in a couple of years. But the third example is, let's look at FRP. Let's take away the steel louver in its entirety, put in an FRP louver, and let's see what that does. So looking at the cost savings, it's real stuff. So the light blue line, that is basically let's just maintain. Let's continue to apply labor. Let's continue to apply materials every year, all the time. Every chance we get into port, we're going to deal with these louvers or those louvers. So it's a constant battle. The parallel line above it, that's switching to a new louver. You have the incremental one-time acquisition cost, but you're going to continue that habit of cleaning, blasting, painting, and welding. So that's what's being done for the most part across the fleet. The alternative with FRP is hugely advantageous. You can see that the initial acquisition cost of an FRP louver is slightly higher than a stainless louver if you're buying one part new versus the other. But the payback can be as early as 4 or 5 years. So what we're seeing over a 20-year lifetime, if you're looking at a relatively new ship, you could see $1.6 million of savings independent of all those other costs of just dealing with the work. So this is just a straightforward head-to-head comparison. It's really compelling. The additional savings you can realize go beyond just dealing with one ship at a time. So if we have a planned approach to this and said, okay, let's look at all the AKEs that are out there in the fleet. Okay, are there commonalities? Are there the same size openings on this ship and that ship? Are they true sister ships? If so, then the planning aspect of executing a project can be kicked into overdrive, and we can get everything ready for the ships next time they come into port. So a little bit of advanced planning can make these savings grow even further. Future opportunities. So louvers, I think it's a compelling argument. It's a pretty obvious way to save money and to avoid costs of maintenance. There's other things that can be done. Discussions with Carderock, discussions with NAVSEA are looking at other things on the ship. Railings, stair, treads. There's already pieces being put in place to replace traditional steel parts, but there's an endless opportunity, I believe. Other things that can be done, there's anti-slip of applications you can put onto materials to heighten the safety of these parts so people don't slip on them when they're wet. Those are very easy to apply, and they can even bond into the base FRP material for added resistance. One of the things that can be done as well, those shipside louvers typically protect an air intake filtration system. So those air intake filtration systems are doing the work of removing water droplets and removing salt and sand particles from the air going into a combustion turbine. Those pieces are also made out of stainless steel or aluminum, depending on which type of ship. So the vanes that remove the moisture, those can also be made from composite materials as well. So applying the same base material, the same manufacturing technique to a different product, so that in essence the whole air intake system from shipside protection through the moisture separation can all be done in composite materials. So I think the big activity here is let's look at what can be done on new ships and what can be done on retrofits of old ships. So there's really two ways to look at it. It's difficult to get spec'd in for new ships. We know those specifications take years or decades to come together, but it's a very practical approach. And with the pedigree of this material that's been used in different applications, even besides the louvers, there's lots and lots of technical backup for the performance of these raw materials. So in conclusion, we do have with the Navy over 10 years of application of these FRP louvers aboard LPD. Other than some paint challenges that have become evident, the base materials have been sound. They're remaining very good, strong condition. The resistance to UV has been excellent. So that 10-year basis can take us forward to the next 10 and beyond. Standard radar cross-section, really depending on the ship's mission. The standard generic louvers are more economical, more simple to make, but the radar cross-section feature can be applied selectively to different louvers and can be put into place aboard ships that require that. About the radar cross-section louvers, those are tested on the way out. So on the way out of the pultrusion process, the Navy comes in with a measurement device, checks each piece and tells us if it's okay to go to the next stage of manufacturing. So there is an acceptance rejection criteria for radar absorption of the pultruded pieces before they go into detailed manufacturing. So again, slightly higher initial cost. It could be maybe 5 or 10% higher on a generic small louver, or it could be maybe 15, 20% higher on a larger, more complex system. But it really depends on what size, what shape, and if the radar cross-section material is applied. But that initial cost is really overcome very quickly. So 4-year, 5-year payback is more than reasonable. It's outstanding in many cases to justify their use of these devices. We're seeing, again, with 10 years of life, no breakdown of the base materials. It's almost too obvious to apply these in some cases. So we've got to get this going. We've got to talk to our colleagues and our peers and look and see what are the other challenges. Maybe there's things that we're missing, from my perspective, that need to be overcome, and I think they can be. And again, the other thing, really, if you look at ship availability, is the time that things take. One of the challenges when ships come in for refits and for refurbishment work, schedules never go according to plan. Schedules overrun, things are requested at the last minute, and those become more and more expensive than the baseline costs that were expected. So looking at pultrusions, it's a true proven method to get the product produced in advance, get it there on time. We typically will look at trying to deliver a month ahead of schedule so things can be stationed and staged at the port. So that's all possible. And I think pultrusion really gives you the surety of schedule and the flexibility to do all the different size louvers that are required for these. Ultimately, what we're trying to do is we're trying to get the grinders out of the hands of the sailors. We're trying to get the paintbrushes out of the hands of the sailors and get them focused on their mission. That's really what it's all about at the end of the day. So, well, thank you, everybody. I appreciate your time today, and thank you.